Hi, welcome. Today I'm going to talk to you about a little bit about the notion of uncertainty, entropy, something about how heat engines work and how hurricanes work like heat engines. In a very fundamental way, I'm going to tell you why you should worry about entropy because that's what decides how much insurance you pay in the place you live depending upon hurricanes. Okay, so the hurricane part of it is a little bit, is for fun. And a lot of the stuff that from hurricanes I got from this very nice book by Kerry Emanuel on hurricanes and their history and their science. The picture that you see in front of you is actually Hurricane Floyd, and you can see beautifully how it spins, and there's a huge amount of clouds and so on. Just to be consistent, my name is Arun Srinivasa, and I'm a professor in the Department of Mechanical Engineering at Texas A&M. Okay, so let's look at what hurricanes are about and why we are interested in them. So if you looked at one of the largest hurricanes to ever hit the US in terms of devastation, it was the hurricane of Galveston in 1900. And just to tell you how wrong people were in terms of forecasting this hurricane, this is what Isaac Klein, the local forecast official and section director of the US Weather Bureau in Galveston, Texas, said. The opinions held by some who are unacquainted with actual conditions of things, that Galveston will at some time be seriously damaged by some such disturbance, is simply absurd. That's what he said. Then 8 a.m. on September 6, 1900, the storm will probably continue slowly northward, and its effect will be felt as far as the lower portion of the middle Atlantic coast by Friday night. That's what they said. And then by Sunday, there was utter devastation. Okay, so being able to figure out how hard hurricanes hit and where they hit is really very important. Just to get you some basic ideas, in 1876, storm surges in the Ganges Delta, which is modern day Bangladesh, killed 100,000 people. The average hurricane precipitates about 1 trillion gallons of rainwater a day and produces 5 times 10 to the 19 joules per day. Sorry about the misspelling, just one of those things that got away from me. Just to look at this, what the radar data looks like. You can see that it reaches pretty far up, several kilometers up into the sky. This is the rain, and you can see how the rainwater looks. This region here is actually the eye, and somewhere out here there is a plain. Okay, you can fly through the storm. This is where it rains very, very heavily, extremely heavy rain, and then there's quiet. Okay, the first flight into a hurricane was by Joseph B. Duckworth, head instructor, instrument flying instructor school, Bryan, Texas, January 27th, 1943. Okay, so this is what a hurricane looks like. The question is, how does it form, how does it work, and so on. So let's take a look. By the way, just to get you an idea, flew an open AT-6 trainer into a hurricane approaching Galveston on a dare. If you want, you can go take a look at Joseph B. Duckworth and you'll learn quite a bit about it. How does a hurricane work? So first question is, where does a hurricane get all its power from? Second question is, how do they operate? That's the easy question to answer is, how does it work? And I'll tell you how it works. The hard question to answer is where it is headed and how does it start? And what is it likely to happen if conditions change due to global warming and things like that? So I'm going to touch upon some of these things. I'm not an expert on the global warming side, but I can tell you a little bit about what it is. Some of it is somewhat common sense knowledge. But the main thing is no indication of an increase in the number of hurricanes, but intensity of the hurricanes have increased. So this is what people talk about, the fact that weather pattern intensities have increased. We will answer only the easy questions, will not answer the hard questions, and in a somewhat simplistic way. But if you want to understand this, you need to understand how heat engines work, how Carnot cycles work, and all this thermodynamic stuff that you thought was boring. We'll start with it in a somewhat different way. So what's the objective of this talk? To start out by talking about uncertainty and a scale for uncertainty. We are going to apply this idea to the description of gases. This is bizarre, no? But you will see that how it's connected. Then I will describe heat engines. Then I'll describe how a hurricane works. That is an excellent example of a heat engine that's almost close to a Carnot cycle. I'll show you some qualitative reasoning about what will happen under different conditions. So first up, entropy. This is a puzzling concept. I'm going to tell you something fairly simple about it. So let's start with something that has got nothing to do with thermodynamics at all, and it's the following question. You walk into an exam room and you've forgotten that there's an exam, you're completely unprepared, but magically you know who has answered what in the question. So the question is, what would you choose? Something like that. So imagine you have 4 questions in the exam. Look at the answers that people have given. Answer A, answer B, answer C. And question 1, 100% of the people have answered A. So from your point of view, it must be obvious to you that if you pick A, you're at least going to be consistent with the others. But as you go, by the time you get to question 4, it's clear to you that nobody knows what the answer is because it's all over the map. This is what we mean by uncertainty. How sure are the students about the answer? So what I want you to do is pause this video and go and answer the following question. Rank the students' uncertainty with respect to each question. Just go and rank it. Just intuitively. Okay, pause it, do that, come back. Did you pause it and come back? Very good. So now let's see if we can figure out a way of talking about it. So if you look at it, uncertainty is an intuitive concept and can be ranked. For example, students are absolutely certain about question 1. Students are absolutely uncertain about question 4. Students have higher uncertainty of question 2 than question 3. Can you see question 3, more people are thinking C is the answer, but question 2, 50-50. Can you see that? Right? But definitely less than, they all think that C cannot be the answer. So Q2, they are less uncertain than Q4. You see what I mean? So my ranking would be Q4 is the most uncertain, Q2 is the next uncertainty, Q3 is the next one, and Q1 is the last. Did you get the same thing? If you did, then you can agree that there is a reasonable idea that uncertainty can be something that's intuitive and can be ranked. Okay, now let's get more precise about this kind of an idea. What do we mean by uncertainty? We have an intuitive notion. So let's formalize this. I have a system, and it's not necessarily physical, which can be in many states. In this particular question, the system has 4 questions, and each question, the state is A, B, or C, answer. Okay. The microscopic state is which student has given what answer. That's what the person who's giving the exam gets. Right? What you have on the other hand, you have only some aggregate information. How many students answered question 1? How many students answered question A to question 1, etc. The question is, how many microstates correspond to a given aggregate data? What do I mean by that? In how many different ways can I satisfy the same aggregate information? For this, you need combinatorics. What I mean by this is that the more the number of ways, the less sure you are about who answered what. Right? Let's see if we can compute this by using combinatorics. Let's pick question 3. Total number of students are 100. Number of students answering A was 20. Number of students answering B was 0. Number of students answering C was 80. Let's assume that the students are all answering these questions independently. So what happens is, the number of ways, if that's all you know, and you want to assign a particular answer to each student, each of the 100 students, you want to say, okay, student 1 answered A, student 2 answered B. No, nobody can answer B. Student 2 answered C, and then so on. How many ways can you divide these 100 students into groups of 80 and 20? Turns out this is a combinatorics problem. And that tells me how well can I know who answered what. Because the more the number of ways in which I can assign, the less sure I am of any particular student answering a particular way. By the way, just to get you this thing, the number of ways in which you can do is 100 factorial divided by 20 factorial times 80 factorial. And that's a monstrous number. 53598337040380968297. That's how many different ways you can assign answers A and C to 100 students such that 80 students answered A and 20 students answered B. If you think that's a big number, let's look at question 4. In question 4, N1, N2, N3 were all 33. So for question 4, 100 factorial over 33 factorial, 33 factorial, 33 factorial is that mind-boggling number. You can see that there are more ways to put the 3 questions for question 4 than for question 3. It's too big, so what we are going to do is we are going to take log so that we get manageable sizes. Okay, now we are ready, because now we can say uncertainty means how many different microstates can I assign to a given macro state. So macro state means aggregate information, this kind of aggregate information. Microstate means how much did each person get, what answer did each person choose, right? So let's look at that. If there are more microstates, then we are less uncertain about who did what. So now we have a way of measuring it. N equal to total number of students, Ni equal to number chance answering choice I. Pi is proportion or probability of student answering the ith question. So our entropy measure is log n factorial over ni factorial, n1 factorial, n2 factorial, n3 factorial, which is pi of ni factorial. You know what pi means, like product. We are going to use an approximation for this. This is called Stirling's approximation, which says log n factorial is n log n roughly. And you can see why that is if you muck around with it. But then I can sort it out very nicely as saying minus n times pi log pi, I equal to 1 to 3. That's it. This is what we mean by entropy. So this minus pi log pi summation will be called entropy, times number of people will be called total entropy of the system. Let's see if this gives us a real measure. So the main things are, if only one thing is guaranteed to happen, there is no uncertainty, right? If everybody answers A, there is no uncertainty. You know how to assign everybody that thing. If all things are equally possible, you have the maximum amount of uncertainty. Let's look at an example of something else. Temperature distribution in College Station. Average temperature over the year is 70 degrees. Super balmy weather. Standard deviation is 30 degrees. So you could get as high as 100 degrees or as low as 40 degrees. Right? And much higher or much lower. So this is standard deviation. So for example, you can get that kind of standard deviation is exactly half the number of days. That is, January to July, you have 70 degrees, and then July to December, you have 40 degrees. 140. Right? There is no uncertainty. On any given day, you know exactly what the temperature is, if that is a distribution. But if all you know is average and standard deviation, how predictable is the weather on a given day? That's what we mean by entropy. Given the average and standard deviation, how well can I assign a given temperature to a given day? That is really what I mean by uncertainty. That makes sense to you? That's how it works. Okay. Now let's see if our measure of uncertainty really works. So we saw that. So for any probability distribution, we know what is meant by mean, mu. We know what is meant by variance. And entropy is also a measure for a probability distribution. Minus I equal to 1 to n, pi log pi. That's entropy for a probability distribution. Okay, this is our definition. Does it really work? Let's look at our answers. Answer A, probability distribution is 1, 0, 0. Answer B, question 2, probability distribution is 0.5, 0.50. Question 3, probability distribution is 0.2, 0, 0.8. And 0.33, 0.33, 0.33. Let's calculate the entropy. So sum of minus P log P. So minus 1 log 1, minus 0 log 0, minus 0 log 0. If you get it, you'll get 0. because 1 log 1 and 0 log 0 both give you 0. So it is 0. This one is 0.5 log 0.5 plus 0.5 log 0.5 plus 0 log 0. Negative of all of that gives you 0.693. Try it. This one will give you 0.5. Question 4 will give you 1.096. So let's see. This had the highest entropy, so most uncertain. This had the second highest, second most uncertainty. This had the third highest, third uncertainty. This was absolutely certain, entropy was 0. That makes sense to you? That's how it works. So you can see that for any probability distribution, I can compute the entropy and it will tell you how uncertain the probability distribution really is. Very good. The idea was originally proposed by Boltzmann, and entropy is 0 only if only one event occurs. Entropy if maximum if all events are equally likely. It's always non-negative. If there are many different distributions of independent events, then the entropy is the sum of the individual entropies. This is a very key thing. And then it was shown that there's only one function of the distribution that has these properties. Then there are some minor properties, and that's this function. By the way, this k is just a normalization factor, so that I get reasonable numbers. So it's just a multiplication factor. For example, if this number gets very, very large, then you want this k to be very, very small so that I get reasonable numbers for s. That's how it works. Okay. So typically, k is called the Boltzmann constant, for example, and it is 10 to the minus 34. So I want you to understand that this pi log pi will get to sizes of 10 to the 34 or higher. So it's a very large number. Okay, this is our idea. Okay, that's really critical. So, and pi, just to remind you, is a probability that the ith event can occur, or the proportion of times in which the ith event occurs. Up to now, nothing at all about physics. This is all pure statistics. Now we will look at physics. So before we do that, because we need this thing, if all events are equally likely, then S is equal to minus k log p, where p is the likelihood of that event. If the events satisfy a Gaussian distribution like that, then entropy is minus k integral of p log p dx. If you do that, you will get k log of the variance, standard deviation plus constant. That's what you will get. If you try to integrate this p log p dx, you will get x squared e to the integral minus x squared dx, and then if you do all integration by parts and this, that and the other, after a lot of effort you will get this. We don't really care about this constant for our purpose, but it looks like k log variance or k log standard deviation, and it makes sense, no? For a normal distribution, the more spread out it is, the more uncertain the distribution is. Okay, very good. Now, our next thing we are going to talk about is application to the description of gases. So I have a model for a gas. Let's see if I can make this run. Yeah, you can see all the gas molecules dancing around, right? This is my gas model. Right? I'm going to assume that the location of the particle is equally likely anywhere in the box. It's not particularly preferring to be anywhere in the box, so it's equally likely. That's my assumption. What is the entropy associated with the location? Well, that's easy. Probability of finding a particle in a given location is inversely proportional to the volume. That's obvious for you, right? So each event is equally likely. So the entropy is minus k1, where k1 is some constant, log of 1 over v. This is the probability of finding it in a box, somewhere in a box of volume v. So that is k1 times log v. That was easy, right? Very good. This is called configurational entropy. This tells you uncertainty in location. Okay? Uncertainty in location is called configurational entropy. Now, on top of it, I want to know how fast the molecules are going. By the way, configurational entropy is what changes when we expand or compress the gas. If you compress the gas, volume goes down, entropy goes down. If you expand the gas, volume goes up, entropy, configurational entropy will go up. So expansion and contraction allows you to change the configurational entropy of the gas. We are now going to look at velocity distribution, and in this I am going to state something which is technically not completely correct, but it's good enough for our purpose, which is that the velocity of the particles in a gas have a Gaussian distribution with zero mean, because a box is not going anywhere. How do I know it's a Gaussian distribution? This takes a lot of effort. This is velocity, not speed. Speed follows something called a Maxwell distribution. Velocity follows something called a Gaussian distribution. Why this is takes a lot of effort, I'm not going to talk about. Okay, this you have to take on faith. If you do that, the variance of this thing is integral of the square of the velocity, no? Speed squared, integral of speed squared. This is average square of the speed. Can you see that? That's the average square of the speed. That is the variance. Temperature is variance. Variance in the velocity distribution is called temperature. So temperature is proportional to the speed of the thing. And entropy is log of the variance. I told you that, right? So it's k times log of variance plus constant. So which is, since temperature is proportional to variance, this is some constant times log of theta plus constant. Who cares about these constants? The most important thing is the uncertainty in the velocity is k2 log of temperature. So I introduced two ideas. Temperature means variance in the velocity for this particular case. Entropy is proportional to log of variance. So entropy is proportional to log of temperature for an ideal gas in this model. Right? This thing is called thermal entropy. It is a measure of the variance. We talked about this. By the way, variance is also, because it's a square of the velocity, square of speed will give you kinetic energy, no? So variance is also proportional to the kinetic energy of the particles. For a gas, the total energy, kinetic plus potential, equals kinetic energy, because no potential energy for the particles. Hard sphere model. So if there is no potential energy, then the internal energy, which is the total energy of the gas molecules, equals some constant times the temperature of the gas, because temperature is proportional to kinetic energy. This is a very important idea. Right? We're going to put all these things together, and the entropy associated with the uncertainty in the velocity distribution is called thermal entropy, and that looks like this: k2 log theta plus constant, because variance in the uncertainty is proportional to temperature. We are now going to assume for a gas that its position and velocity are uncorrelated. How fast it goes does not depend upon where it is. Strictly speaking, this is not really correct, because as it gets close to the wall, things will change, but we'll assume it's reasonably okay. If you do that, your total entropy looks like k1 log V plus k2 log theta, configuration and thermal. That's it. So we got what is meant by entropy of a system. Now we are going to get to the next step. We'll do some qualitative reasoning. Okay. Let's check. What will happen to the entropy if I expand the gas at constant temperature? Well, if the temperature is constant, no change in the thermal entropy, correct? But if I expand the gas, configurational entropy will increase. So total entropy is getting higher. This is called an isothermal process. In an isothermal process, configurational entropy will increase. Okay, that's obvious, right? And you notice you didn't have to do any calculation. What happens if I cool the gas at constant volume? Volume is constant, so configurational entropy is fixed, but thermal entropy will decrease because I'm cooling. right? So you can see that the total entropy will come down. What if I expand the gas while I cool it? Well, if I expand the gas, configurational entropy will go up. If I cool the gas, thermal entropy will go down. You're with me? So I can adjust it exactly right so that the total entropy doesn't change. So what I do is I swap one type of entropy for the other. And that's how a reversible adiabatic process works. This is called an adiabatic process. We'll see why it's called adiabatic, but at this stage, this is a reversible adiabatic process. I expand and cool, or I contract and heat. And this is isentropic, constant entropy. And how is that possible? Configurational entropy compensates for thermal entropy. That's what is going on. Very good. What happens to entropy when something melts? Well, think about the following. When a material is a solid, every atom is locked up in a cage. That makes sense to you? So you know where the atoms are. So configurational entropy is very, very low because you know where every atom is. Now when you melt it, the atoms start moving around like crazy. The configurational entropy will increase by a large amount. You can do it in such a way that the thermal entropy doesn't change. What happens is when it's in the cage, it's dancing around like this. It's like somebody who is a drug addict who is undergoing withdrawal symptoms. You know what I mean? It's just like that. So the velocity is very high, right? And the spread in the velocity will be like what you're talking about. Remember, that's how it does, like that. But when you open it, the velocity will still be the same. Configurational entropy is more, the particle can move around anywhere. So what will happen is that the thermal entropy can be made to stay the same. So when something evaporates, there will be a large increase in configurational entropy. This is vast increase in the ability of the atoms to move around. That doesn't mean vast increase in its velocity. It just has plenty more space to go. If you are doing configurational entropy change at constant temperature, like this phase change, the corresponding energy required is called latent heat. Temperature times the change in configurational entropy. It's called latent heat. So you can see that the best way to do an isothermal process, expansion, is to do melting or boiling. Because you maintain the temperature constant, you will vastly increase the configurational entropy. That's how you do. Okay, now we are ready to do one more thing. We're going to talk about what is meant by equation of state. So, for a general gas, the probability distribution of positions and velocities are expressible in terms of two parameters: the volume of the gas and its internal energy. In our particular case, entropy is a function of volume and energy. And I'll show you in a second. This is called equation of state. It's actually called the fundamental equation of state. It is not a convenient one, but that's the starting point. If I assume that these variables are invertible, I can write internal energy as a function of volume and entropy. Instead of a gas, if you look at a spring, like a rubber spring, the probability distribution of the positions and velocities of the atoms are expressible in terms of two parameters: the extension of the spring and the energy. So the entropy will be a function of strain and internal energy, or the internal energy will be a function of strain and entropy for a spring. That's how it works. In general, state looks like some function of mechanical variables and entropy. That's what the equation of state will look like. For the gas case, I'll show you specifically. So remember, entropy was this, internal energy was U equal to C times theta. What you do is you eliminate theta. Theta is a parameter. You can eliminate between these two things. If you do that, you will get entropy equals K1 log V plus K2 log internal energy plus constant. This is a fundamental equation of state. You can solve for U and you will get U equal to E to the something. This is your equation of state. Okay, K1 and K2 have various meanings, but I don't want to worry about it. I just want to show you what it looks like. This is the equation of state for an ideal gas, fundamental equation of state. We want to talk about energy equation and heating. So there is a lot of confusion among people. Making something hotter is increasing its temperature. Heating something is not the same thing. Let me give you an example. You put a stove of you put a pot of water in the stove initially, and you say you are heating it, right? So what happens is initially the water becomes hotter and you're still heating, right? After some time, when it reaches 100 degrees, the water starts boiling and evaporating, correct? Vast increase in configurational entropy, you're with me. But temperature will not change, it's at 100 degrees, it's undergoing a phase change. But you're still heating it, right? So we want to be very careful about what the heck we mean by heating. To understand that, we have to do energy equation. So conservation of energy tells me that rate of change of energy must be equal to how much mechanical work you are doing plus how much heat flux is coming in, right? Now, I'm going to use the equation of state and U equal to U of mechanical variables. These are all the mechanical variables, and this is the entropy. So U is that. This part of it we can identify as how much work you can get back, but I will not waste your time with that, but the idea is there. So what happens is, if I move this to the other side, you will see that du ds times s dot equals mechanical power in minus whatever is mechanical power that is recoverable, that can be got back from me, plus heat flux in. This thing is called mechanical dissipation. This is what happens when you rub something and you have friction. You are doing work, but you will not get it back. It's not changing the mechanical variables. Can you see that? So all the mechanical power will become heat. What do we mean by that? I will show you in a second. Mechanically, by the way, mechanical reversible process means power in must be equal to power recoverable. Okay, that's just an aside. So let's look at it. So in a general process, we have du ds times s dot equal to mechanical dissipation plus heat flux. Du ds is defined as the absolute temperature, and you can see that if you compute it, it will turn out to be our same thing as temperature, but I am not going to bore you with that. But the main thing is this: heat generated by mechanical dissipation plus heat flux in equals temperature times rate of increase of entropy. So please note that increasing the entropy is what we mean by heating, not increasing the temperature. The rate of the entropy may increase because I'm increasing temperature, but if the entropy is not changing, that will not be called heating. The entropy has to increase. That's what we mean by heating. Okay, so now we have talked about heating, cooling, work, mechanical dissipation, all these things. Fantastic. Now let's see what happens in a Carnot cycle. So first thing I do is, and I'm going to draw it in a temperature entropy diagram. First thing I do is, I'm going to put a gas in a hot, here's a gas, I'm going to stick it in a hot reservoir and expand it. By doing that, remember, I'm doing it isothermal expansion. No change in, no change in thermal entropy, isothermal. Vast increase in configurational entropy. So it goes from A to B. Right? During that process, T times S dot or T times change in entropy equals heat in. T times change in entropy equals heat in. This much heat I absorbed. This big red block. I got to B. I'm going to cool the gas and expand it. So remember, cooling and expansion will increase the configurational entropy, cooling will decrease the thermal entropy. I'm going to do it in such a way that the total entropy is fixed. So I'm not going to absorb any heat because the entropy is fixed. Remember, I told you heating is changing entropy. So I'm not going to absorb any heat. So it comes down, boom, like that to point C. At point C, I am going to go from C to D by compressing and cooling. So if I compress it, configurational entropy will decrease. And I'm going to keep the temperature constant from D to C. So net entropy will decrease. I'm going to decrease it all the way back to the entropy all the way back to where it was at A. And since this is a constant temperature decrease in entropy, I'm going to reject heat, and that's the blue area. Then what I'm going to do is I'm going to keep compressing, but now I'm going to do it at constant entropy. I'm going to heat and continue to compress the gas. It says expand, it's incorrect. Heat and compress the gas at constant entropy. So what I'm going to do is, I'm saying that in a very casual way. What I mean by that is, I'm going to do isentropic process. It will raise the temperature, but it will lower the configurational entropy. If I do that, net work done equals work, this red area, net red area is work done in the cycle, and efficiency is net red by total red. Remember, total red was this much, and net red is this much. So the ratio of this to that, the ratio of ABCD to the total rectangle gives you the efficiency. So you can see that I can increase the efficiency by lowering this DC or by raising AB. And if you compute that, it depends only upon the temperature. That's called Carnot efficiency. This is how Carnot cycles work. And by the way, I was kind of sloppy in terms of cooling and heating. Please remember, in these cases, I'm talking about lower the temperature or raise the temperature. So I should have been more careful. I shouldn't have called it cool and heat. Cool means lower the temperature here. Heat means raise the temperature here. I'm using that very sloppily after having told you all of that. I'm sorry about that. Okay. So please remember, in this particular one, cool means lower, heat means raise temperature. Now let's look at a hurricane. So you imagine air here, and the working fluid is the Gulf, warm Gulf waters is the working fluid, and that's the hot reservoir. Cold reservoir is outer space. And by the way, a hurricane raises like 14 kilometers above this Earth's surface. So you are actually in the stratosphere, and basically the cold reservoirs are outer space minus 73 degrees. Hot reservoirs are 27 degrees. If you compute the efficiency, you should get 33% efficiency. 300 minus 200 over 300. If you compute that, you get 33% efficiency. Right? How does it work? So, first, along AB, dry air blows over the hot surface, water evaporates. Huge increase in entropy, no increase in temperature. Right? This is the hot reservoir. So, I'm going to absorb a huge amount of heat. Then, I'm going to expand and cools rapidly. So, because H2O is lighter than O2 or N2. You know, dry air is heavier than moist air. Although people say the air is heavy with moisture, it's not correct. Moist air is lighter than dry air for the same temperature and pressure. That's why clouds rise up. And what happens is, the higher you go, the lower the pressure, the gas expands and expands and expands and expands. At some point, it will start condensing. That's the start of the heat ejection cycle. You get lots of rain, everything condenses, and then along CD, the now dry air radiates heat to outer space and drops down. And then from D to A, because it's now dry, as it falls down, it gets compressed. So the way you get compression and expansion in the atmosphere is by raising or lowering. It's run by gravity. Right? It's a gravity pump. Right? And I want you to understand that everything depends upon, outer space temperature minus 73 degrees Kelvin, that's 73 degrees, you are fixed. What matters is what is called the sea surface temperature, SST, the Gulf temperature, because that's the hot reservoir temperature. So what happens? All the work done becomes kinetic energy of the wind. Wind speed depends upon the temperature. This is the whole point of doing this whole thing. And it turns out wind speed is related to hot minus cold over cold times the energy absorbed. This is some calculation. I just want to show you what happens sea surface temperature versus the cold temperature. So if you looked at minus 73, it's somewhere here. If the sea surface temperature is about 27 degrees, you get a wind speed of about 50 meters per second. Okay. If your sea surface temperature goes to 34, 35 degrees, you get a wind speed of about 90 meters per second. Just to get you an idea, 1 meters per second is approximately 22 miles per hour. Right? So 100 meters per second is 220 miles per hour. I want you to understand that that's really, really fast. Sorry, 2200 miles per hour. That's really, really fast. So you are going pretty high here. Okay. So wind speeds increase by about 5 degrees for every 1 degree rise in sea surface temperature, because that will make your engine, carnot engine, more and more efficient. So if you can predict the sea surface temperature, we have a handle on the effect. By the way, if you just look at carbon dioxide, it gives you only 0.5 degree rise. That's all the heat absorbed. But the real deal is this changes in evaporation. The trends indicate sharp rise in sea surface temperature greater than half a degree. This will evaporate a lot of water, and that will entirely change how much radiation is absorbed and how much heat is retained and all this stuff. So you have to understand the water vapor cycle along with carbon dioxide. So when people talk to you about global warming, they're not just talking about carbon dioxide. They're also talking about the knock-on effect, secondary effect of the fact that greater sea surface temperature means greater water in the atmosphere, means greater heat trapping capacity. So there's a whole bunch of internal cycles that are out there. We're done. Entropy is a measure of uncertainty of a distribution. It is given by the formula negative sum of P log P. For a gas, temperature is measure of the variance of the velocity distribution. It's also a measure of the kinetic energy of the molecules. And the entropy of a gas is the sum of configurational entropy plus thermal entropy. The Carnot cycle looks like a rectangle in temperature entropy space. A hurricane is a Carnot cycle between the ocean and outer space. Okay, so you can look at all of these things. If you want to learn more, go and read this very interesting book called Divine Winds, The History and Science of Hurricanes by Kerry Emanuel. National Weather Service website, there's a lot of information on this kind of stuff. If you go look at articles on global warming and hurricanes, you'll see a lot. If you want to learn more about entropy, look at the Wikipedia entry on Shannon entropy. It's quite useful. But be very careful about entropy articles on the web. Most of them are by crazy people. And you have to they will say all kinds of things. So be very careful about that. Excellent book called Thermodynamics and an Introduction to Thermostatics by Herb Callan. And the second part of the book contains examples from rubber bands to radiation. It's a nice example. You'll see a lot of this stuff. If you really want to learn more about this, you should take a class in statistical thermodynamics or statistical physics. Thank you very much.